Welcome back, everyone. I am incredibly pumped for today's explainer because, well, we're looking at something literally foundational yet completely invisible to most of us. Look around you right now. The building you're in, the phone or monitor you're watching this on, the roads outside, none of it exists without one intensely engineered material, tungsten carbide. Today, we're cracking open the EG Hard Metal catalog to explore the hidden metal shaping industry. Trust me, it's going to totally change how you look at global manufacturing. Let's get right into it.
Okay, here's our roadmap for today. We're going on a bit of a hub-and-spoke journey. We'll start with the backbone of precision, then scale up to drilling for oil and mining, heavy impact crushing, precision blades and knives, and wrap up with specialized industrial wear parts.
First up, Section 1, the backbone of precision.
The EG Hard Metal catalog labels their carbide rods as the backbone of precision and durability. And honestly, that is not an exaggeration. These unassuming little cylinders are the literal foundation of the entire industry. See, tungsten carbide is a bit of a unicorn material. It gives you this almost magical combination of extreme hardness and crazy high heat resistance. So when engineers need a tool to just effortlessly slice through solid steel or titanium without melting into a puddle, they start right here, with a carbide rod. These are basically the blank canvases that become the ultra-complex end mills and drill bits powering the world's machining.
But that brings up a really cool engineering question straight from the source material. Are hollow rods stronger than solid rods? Now, if you had to guess, you'd probably think, well, obviously, a solid chunk of metal is stronger, right? But metallurgy is full of surprises, and the answer to this actually dictates how the biggest industries on Earth design their most critical tools. The catalog highlights this massive ongoing debate between solid and hollow rods. Here's the deal. Solid rods give you maximum shear mass and raw structural rigidity, which is absolutely perfect for brute force jobs. But hollow rods, they're often designed with these tiny internal coolant channels. That means you can pump fluids directly to the cutting edge during insanely high-speed operations. Plus, from a structural engineering standpoint, a tube can sometimes handle torsional stress, twisting forces, way better than a solid piece, all while saving weight. So it's not about one being universally better. It's about perfectly matching the geometry to the exact physical stress of the job at hand. Pretty wild, right? Let's move on to Section 2. Drilling for oil and mining. We're scaling things way up now. Enter DTH, or down-the-hole drill bits. Picture this. You're trying to smash through solid bedrock hundreds of feet underground. Standard steel? It would literally be chewed up and spat out in minutes. DTH bits use tungsten carbide inserts to relentlessly shatter that rock. The EG catalog notes they make both high-pressure and low-pressure configurations. Why does that matter? Because extreme extraction isn't just about breaking the rock. You have to manage pneumatic pressure to blow all that debris out of the hole so the carbide can keep driving deeper. And the sheer variety here is mind-boggling. We're talking tricone drill bits, those iconic triple roller things you see on massive oil rigs. You've got carbide button bits, studded with ultra-hard carbide buttons that just pulverize stone. And it's not even just the cutting edges. They also make tungsten carbide nozzles for the oil industry. These nozzles take an absolute beating, blasting highly abrasive drilling mud at extreme velocities. Without these very specific carbide parts, global extraction of water and energy would just grind to a screeching halt. Now for Section 3, heavy impact milling and crushing. Things are about to get intense. Okay, let's translate some of this heavy industrial jargon into stuff we can actually picture. Take HPGR studs, which stands for high-pressure grinding rolls. These are used for crushing cement. Just imagine the shear force needed to crush boulders into fine powder, all day, every day. Next up, VSI rotor tips, vertical shaft impactors. These basically hurl rocks against a carbide anvil to make artificial sand for construction. You literally need tungsten carbide to survive that kind of continuous high-speed impact. And then you have grinding jars used in heavy milling, relying on carbide to break down super abrasive materials without contaminating the final batch. Ultimately, this all comes down to extreme durability surviving immense pressure. And here is why this matters to you and me. It's about keeping the world running. Think about it. If a cement plant has to shut down every 3 days just to swap out broken steel crushing studs, the cost of concrete goes through the roof, and global construction slows down. By using tungsten carbide components, they can keep crushing rock for months on end. It's the quiet hero of operational efficiency. Shifting gears entirely, here is Section 4, precision blades and knives. We're going from earth-shattering force to absolute micro-scale precision. Take a look at the Zund oscillating knife. This is a highly specialized, insanely precise blade for intricate industrial cutting. Unlike those giant mining bits, these are small, razor-sharp, and move at lightning-fast speeds to slice complex materials. Tungsten carbide shines here not just because it's tough, but because it holds an edge way, way longer than steel. In a high-speed automated factory, a dull blade means ruined product. Carbide guarantees a perfect, microscopic cut every single time. And the diversity of everyday stuff shaped by these blades is staggering. Corrugated paperboard, that's literally every delivery box on your porch. Chemical fiber production, that's the synthetic clothing you might be wearing right now. Metal slitting, cigarette manufacturing, packing, printing, almost everything we buy is packaged or woven by automated machines. And those machines completely depend on carbide knives to slice materials incredibly fast without any fraying or tearing. Which brings us to our final category, Section 5, Specialized Industrial Wear Parts. The crucial takeaway here is that tungsten carbide is absolutely not a one-trick pony. Look at how they adapt it for such incredibly specific niches. Concrete pump spare parts, for instance. Wet concrete is super abrasive and will eat right through normal metals. Then there are tungsten carbide valve seats and sleeves that ensure perfect seals under extreme fluid pressure. They even make carbide saw tips and special rods for woodworking. I know, wood seems soft, but at an industrial scale, it generates massive friction and heat. These are custom-engineered solutions for very specific factory headaches. When you zoom out and look at the big picture of this catalog, you realize something huge. Customized wear-resistant tool parts are the hidden components dictating the lifespan of our global supply chains. A multi-million-dollar automated factory is literally only as reliable as the part that wears out the fastest. By upgrading those key friction points to tungsten carbide, engineers prevent catastrophic breakdowns and keep the global economy moving. It's an invisible little upgrade that yields massive economic results. So, to wrap up our journey today, from the cardboard box on your porch to the deep oil wells powering our logistics, tungsten carbide truly is the invisible metal shaping the modern world. We've seen it as the foundational rod of precision, the shatterer of bedrock, the enduring edge of the industrial knife, and the ultimate shield for automated machinery. It's a masterpiece of material science hiding right in plain sight. I want to leave you with a thought to chew on. What would actually happen to our global infrastructure if this single, ubiquitous material suddenly vanished? Our construction, our energy, our entire manufacturing base, they are all secretly reliant on this specialized metallurgy. It just shows you how beautifully complex, yet somewhat fragile our modern world is. Thank you so much for joining me on this explainer today. Keep asking questions, keep looking deeper into the materials around you, and I'll catch you in the next one.